All right, the other thing that we can do is figure out linear and angular speeds. So this is things being thrown in a circle. So if we have, let's say we have a rock on the end of a string and we're swinging it in a circle. We've got two different things going on here. We've got linear speed, which is how fast the actual rock is traveling. And then we have the angular speed, which is how fast our angle is changing. All right, so two different things. Linear speed is going to be the arc length over time, or s over t. And the angular speed is going to be that angle divided by time, theta over t. All right? And so we call that, one thing we're going to want to use here, angular speed we're going to call omega, not w. Don't use w, omega. All right, so we've got a couple different formulas here. And so v, which is our linear speed, we can figure out as r omega, the radius times omega. Another very handy formula here is r theta over t, which is right up here. We might want to use that one as well. All right, so let's take a look here. We've got a clock. We've got a second hand that's 10.2 centimeters in length, and it's traveling around the clock face. So let's find the linear speed. All right, so linear speed is v equals r omega. The r is pretty straightforward. That's 10.2 centimeters. That's the radius of the circle. Now the omega, now we talk about this as theta over t. How many degrees or how many radians does it go through over a certain amount of time? So in this case, we'll keep the 10.2 centimeters. To go all the way around a circle, that takes 2 pi radians. Now how long does it take this second hand to go all the way? Well, it takes 60 seconds. And so if we simplify this, we'll end up with 20.4 pi centimeters per 60 seconds. And we can divide that out. And if we do that, we're going to get approximately, let's see, I've done this already. Let me find where I wrote it down. Example 6 is 1.068. And here's where the units come into play. We want to keep track of these. Centimeters per second. Because if it was minutes, it would be a much different number. If it was meters, it would be a much different number. So we need to have the units here for all of these problems. All right, so go ahead and try it yourself for 111. And let me move this out of the way for you. All right, a circular power saw has a 7 1/4 inch diameter. I'm going to call that 7.25 inch. And it rotates at 5,000 revolutions per minute, 1 minute. All right, so if you were able to say that that is omega, you're in good shape, because omega is angle per time, theta over t. All right, so the first thing, find the angular speed. We're almost home here. Omega equals 5,000 revolutions per 1 minute. But I didn't write down revolutions because it doesn't want it in revolutions, it wants it in radians. How many radians are there in a revolution? There's 2 pi. And that's all we need to know. We'll finish it up. That's 10,000 pi radians per minute. And so with that, we can figure out B, because we want to find the linear speed of one of the cutting teeth as they contact wood being cut. Find the linear speed in feet per minute. All right, so it doesn't really matter. This 24 cutting teeth is kind of throwing you off. Any of the teeth are going to have the same linear speed. Anywhere on the circle is going to have the same linear speed. And it's defined by V equals R omega. And the radius is going to be 7.25 divided by 2. Now that's in inches. This problem wants it in feet. So how do we convert? Well, there's 1 foot in 12 inches. This is unit analysis. We want to cancel out the inches. And then our omega, we've already determined that there's 10,000 pi radians per minute. All right, and we do want this problem in minutes, so we just need to multiply it out from here, and if we do that correctly, we're going to get approximately 10,933 feet per minute.